So, here we have Matthew Wilcox talking to us about the future of non-volatile memory. Matthew has been working with Linux for 13 years and solid-state drives for 4. He's the author of the NVM Express driver and a participant of the NVM Express workgroup. So, here we go.
Thank you. Hi, so I'm here to talk about the future of non-volatile memory. Some of you may think of NAND flash when you think about non-volatile memory. It's true, it is, but there's lots of other kinds of non-volatile memory that I'm hoping to cover in this talk today. So I want to start talking about the NVM Express standard that I've been working on for the past 2-3 years now. It's a standard for talking to non-volatile memory across the PCI Express bus. And the genesis for this, the perception of the need for this was that there were a lot of companies coming out with their own PCI Express cards with NAND on them, and every single one of them had a different interface, which meant that there was a different driver for each of them. And this is a huge headache for manufacturers because they want to have multiple suppliers and be able to switch from one supplier to another in a way that's pretty much transparent to their users. You know, if Seagate's drives aren't performing the way you want them to, then you can switch to Fujitsu drives or Maxtor drives, or with a Serial 80A drive, very easy. There's a standard interface. Everyone knows how to talk to it. You can just change your supplier at the drop of a hat. With an NVM Express device, so with a PCI Express device with a non-standard interface, you've got to go to the hassle of requalifying the driver. You've got to come up with a migration plan for your customers who have all their data on one and they need to switch to another, and maybe the name of the device changes and their scripts break. It's just a huge pain. So the NVM HCI working group set out to create a standard that everyone could build to. We would have one driver and everything would work much better. As my introduction said, I participated in this work group. I wrote the Linux driver for it, and I designed some of the interfaces for it. While PCI Express cards were the original motivator for NVM Express, there's also a push to support NVMe in a drive form factor as well. There's a number of advantages for drives over cards, including customer familiarity, easy hot swappability, and support for dual-ported drives. We are expecting to see PCI Express drives shipped this year, and more to the point, PCI Express drives implementing the NVM Express standard. The Serial 80A workgroup has come out with a statement saying, okay, our next thing is SATA Express. And if you look through the press releases for what SATA Express is, it says we're going to start talking PCI Express over the Serial 80A connector. So, and the PCI Express thing on the other end will either be the AHCI, which is the standard SATA control that everyone's got in their laptop today, or it will be NVM Express. And the statements, the PR statements then go on to say that NVM Express has these advantages, and the AHCI has these other advantages. So that's one aspect of what's going on in non-volatile memory this year. It's evolutionary. It's not really revolutionary. We're sticking to a familiar model where drives present blocks to the host. I think it's a really important evolutionary step. I'm proud to have been part of it. It should lead to better devices for customers. It should lead to cheaper devices. We're cutting down the number of connectors that we have. But what I really want to talk about in this talk today is something that's going to take a little longer to happen. There's a lot of other cool stuff. There's a lot of other cool stuff that's going on. Excuse me. There's lots of really other cool stuff that's going on with the mobile next generation form factor, for example, the ONFI interface, the NAND die shrinks. I decided to cut all that out of my talk today because the stuff that I'm going to talk about is what's, I think, really interesting. I want to be sure that we've got time to discuss it properly. The organizers made it clear that they're looking for us to present work that's still in progress. So I'm looking forward to receiving some ongoing and noisy feedback during this part of the presentation, because very little of what I'm going to be talking about is set in stone, or silicon for that matter. So every couple of weeks, I look at my favorite tech news sites, and I see some new announcement that replacement for NAND has solved some major problem that was preventing it from finally getting into your hands. And the story tends to include a note that NAND is running out of steam, and we're surely only a few years away from hitting a brick wall. You'll find this if you go back 5 years. We were only 5 years away from where we wouldn't be using NAND anymore. I think if you go back 10 years, you'll probably find that we were 5 years from where we wouldn't be using NOR flash anymore. And okay, so they got that one right, but you know, NAND has kept going so far. I mean, well, one day I'm sure it will be true. Well, we can't keep scaling down NAND indefinitely. You know, we're already at the point where the difference between a 0 and a 1 is about 10 electrons on a gate. That's kind of terrifying when you think about it. I was talking to someone from a flash vendor who said, our nightmare scenario is that someone powers off our device and drives it slowly from, well, he said Death Valley, but for this audience, I would say Adelaide to Perth in the middle of summer, and then powers it back on when they get there a couple of weeks later and expects their data to still be there. NAND is not long-term storage. NAND is fast. NAND is awesome. NAND is not archival quality. Keep your NAND devices powered on. They are actually busy doing useful stuff. But the aspects of the technologies I want to talk about today is that they're offering close to DRAM speeds. So for the purposes of this talk, we're going to make two assumptions. One is that one of these, and by the way, I got the names of these technologies from Wikipedia. These are the ones that Wikipedia thinks are going to make it. This is not these. So it must be true. It must be true, and this is not. These are the 4 technologies that my employer are investigating. These are ones that the internets think are going to make it. The other assumption that I want to make is that once these technologies get to market, offering closer DRAM speeds, that the CPU is going to start to treat it the way that it treats DRAM. That is, instead of having a block-based interface where the CPU says to a controller, please DMA that block from here to here, the CPU just loads from it and stores to it. So it's going to be a cache line accessible device, rather than needing some kind of API that gets between, you know, the CPU and the DRAM. Because I think this will be a truly revolutionary step in the industry. So,
you don't know how to program it?
That's right. So okay, you've got some persistent memory. How do you allocate it? Suggestions? Really? No suggestions? Malloc, thank you. Yes, no. People who suggest malloc haven't thought about what happens for the life cycle. You allocate some memory, okay, good. Then the machine goes down, someone tripped over the power cable. You plug the power cable back in, you start the application up again. Surely you want the memory back, since it's persistent. Surely you want the memory you were using last time, and not the new memory, and not some new memory. You want to get the memory back that has your data in it.
Why did it boot? Isn't it persistent? It should have just come up in the same state.
You don't. Yeah, your CPU is not persistent.
Assumptions as to how things work, right?
Your CPU is not persistent. Your memory is persistent, but your CPU doesn't come up with all its registers intact.
But you checkpoint regularly, right?
Checkpoint what?
The CPU state.
And all the device states.
And all the, yes, exactly, the CPU state, all the device state. We are not currently thinking about a model where the CPU is going to have all of its internal state checkpointed. Because that's really hard. So, given that malloc is the wrong answer, the next thing people often talk about for exposing persistent memory is create a block device. And then, yeah, okay, so you can open up that block device, and somehow you know exactly where on that block device your memory was stored, and so you can mmap it. But works, but then all applications on the same machine have to cooperate so that they don't either inadvertently or maliciously overwrite each other's data. I don't know how many people in this room remember the old a.out shared library model, but there was a registry maintained by a person, and if you wanted to create a new a.out shared library and distribute it, you had to plead your case to that individual and say, this is how many bytes of shared data that I want currently. This is how big I think it's going to grow in future. Can you allocate me this much space in the global shared registry that all libraries ever will fit into? Moving to ELF was a great advantage. I'm certainly not interested in creating some kind of registry like that where all applications ever will keep their data. Not when there's already a perfectly good interface for persistent memory. While if you use a normal file system, you mmap a file and that causes the data to be paged in, and then later when your modifications get written back out again. This is at least a model that some applications, not all, some applications really don't like the mmap model, but a lot of applications are familiar with this. You can go and look at a man page today, and you can figure out how to use this. My point of view is we need to present this stuff to applications through a file system API. Either we need to use an existing file system, or we need to build a new one. Existing file systems are heavily built around using the page cache. It would be ludicrous to use the page cache for persistent memory.
Burn the heretic. Sorry, I'm just channeling in this.
Oh, fair enough.
You don't just want to stick a tempfs on persistent memory?
No. Tempfs isn't good. Tempfs actually uses the page cache more heavily than anything does.
It just doesn't have a backing device.
Yeah, you want to start, copying 4K from this persistent RAM to your dynamic RAM, and then copy that 4K back again when it's dirty.
Let's implement a global O-direct flag.
A global O-direct flag, that's a great idea.
Sorry, I'm just self-responsible.
This looks like DNA buff, the same stuff we use for the graphics memory, right? You want to open a device, give you a file descriptor, and you mmap the pages that are behind.
Exactly, yes. Existence proof. Keith has already done this for graphics. It works.
It's not very non-volatile.
Yes, you have a slightly different set of problems. Yes, you probably don't want your machine to come up and the very last thing you were looking at is now being displayed to the screen again.
No, that's very popular at home.
teenage boys everywhere would be very unhappy. So, yeah, like Keith said, we want to point a TLB entry at the persistent RAM, just let the CPU get on with doing loads and stores. It's my belief that the changes needed to a file system, to an existing file system, to make this work are going to be ridiculously intrusive. I had a quick chat with Dave this morning, and he persuaded that maybe some file systems are not quite so wedded to the page cache as others, particularly those that maybe came from a different version of Unix originally and aren't quite so tightly tied to Linux. And also, on the other hand, somebody noted yesterday that Btrfs is still 2 years from being production quality. So what are the odds that any file system we start writing today is going to be production quality within the next 5 years? I mean, I'm thinking it's probably a fairly simple file system to write, certainly in comparison to something like Btrfs that's trying to be a general purpose file system that works for everything. But then you look at stats again. I was talking to Dave, and he said, yeah, I fixed a bug recently that was introduced in the third ever commit to XFS back in 1993. You know, writing a production quality file system is a major undertaking. And everyone I've talked to has their own opinion about this, and yeah, it's going to be a tricky conversation to have. And I think we may actually want to create two teams, each start running in different directions and see what happens. And maybe one way of doing it would be better for some applications and one for others. I mean, I've certainly got 3 different file systems in use today on my laptop, and I suspect I'm not the only person who's using, you know, every major Linux file system across every machine that they have in their lives. So, moving on to some of the other difficulties we're going to have by avoiding the page cache. There are some corner cases in Linux which really expect memory that the user can see to be described by struct page. So Keith, perhaps your expertise in this field might be useful. Have you ever tried doing ODirect writes either to or from the DMA buff?
Why would I do a write to it? I only access it via nmap.
Right. Yes, you nmap it, but then the thing do a write to disk, giving it do an ODirect write to disk, passing it the addresses that are in the DMA buff. Yeah, that's not good. It's not going to go well. Yeah, there's a
Actually, it might work.
The way ARM does this is it turns off so it flushes it. That's the problem.
Yeah, but you don't have a struct page for these DMA buffs.
Yeah, you do.
You do?
Yeah, absolutely.
You create them?
Actually, the struct SG list, scattering out list for all the pages in the DMA buffers. Yes.
Where did you get your struct pages from?
Well, it's backed by a physical page.
Yeah, they're backed by physical pages. Just allocate struct pages for them.
Okay, you allocated the struct pages. Okay, that's probably what we're going to have to do.
In my case, I don't have to because the pages I'm using are actually physical memory pages. Struct pages were already allocated, but there's no reason we couldn't allocate them.
Oh, of course. This architecture steals some of the physical RAM. Right, so we already created a struct page for them in memmap.
We also have the same structure for GPUs that have onboard VRAM. They allocate separate struct pages for that.
Okay, so that would work then. Okay, cool.
You want a struct page for anything you're going to pass around.
You really do. There are a lot of bits of Linux that assume you've got a struct page that can describe any piece of RAM.
Intrinsic memory when you my struct page.
Yeah. So we're going to have to do that. All right, next problem. Linux really sucks at sync.
Just less than everyone else.
So if you do call msync brackets msasync, because there's a whole bunch of different flags you can pass to msync, but msasync assumes your file system uses the page cache. and the application which calls msync, and msync MSAsync is supposed to kick off I/O. And there's a comment in Linux that says, we've got the page cache. Everything's going to be fine. We don't actually have to do anything here. So it's this giant no-op. And the assumption is that the application is going to then do some other kind of sync, like fdata sync, to actually start the I/O. Which I can't quite follow the logic of this comment. I read it 3 times last night. It's like, no, I still don't get it.
Really, what does synchronization mean?
It means at some point in the future, and you don't have to tell me when, I would like this stuff to hit disk.
Right now.
No, not right now. Just some point. Yeah.
I would like at some time
In some of the operating systems, there's basic propagation that dirty bits out of the hardware page tables into the struct pages so that they can then be flushed.
There's lots of applications where we want that kind of behavior. We just want to say, this needs to be synced to disk at some point, and I need to know when it was synced, but it doesn't have to be right now.
Yep. Yeah. So anyway, the other option you can do is a synchronous sync. You can and what that does is it loops, it looks for all the files that are covered by the range you pass to msync. You give it a start and a length, and you say sync everything in this range. And what Linux does under the covers is it finds all the files that covers and calls fsync on each of them. So it's just a really inefficient way of calling fsync because it has to take the mmap semaphore, look up which file or files contain that, and then calls into the VFS. So you might as well just call it fsync directly, assuming you know which file it is, and you probably do because you've probably got that information around in your application. Okay, so fsync, right? That's great. Well, no, fsync synchronizes more than you need. It synchronizes everything related to that file, including all the metadata like timestamps, and that can be really inefficient, which is why we came up with fdata sync. Now, fdata sync is true. It won't force things like the modification time you don't really care about to get written out. On the other hand, like fsync, it does force all the modified data in the file to be written out rather than just the bytes in, imagine you've modified, 3 bytes and you say, sync those 3 bytes, and it says, actually, I'm going to sync everything in that file. So, yeah, great, thanks. And then we've got sync file range, which was, if I were Linus, I'd start speculating what kind of illegal drugs the person who wrote it was on. Sync file range. I mean, this is not a POSIX syscall. This is something that some flinging monkey decided to add. It's only guaranteed to work if you're overwriting existing data. If you extended the file, it doesn't work. If you're filling in a hole in the file, it doesn't work.
And not only that, it doesn't flush your disk caches either.
Brilliant. It doesn't even flush your disk caches. So, I can't imagine there's anyone. There must be one application somewhere that uses this, and it does exactly what it wants. But I just wish to put the name of the application in because I can't see it. I should have gone through the Git logs and seen the name of the submitter. I'm fairly sure. Google. Ah. So yeah, everything sucks. In addition to Linux sucking at sync, humans suck at sync, and this is going to be a huge problem for us. I mean, Tridge and Rusty are not exactly what you might call a normal programmer. I mean, they're pretty big brains, and yet their code, TDB, turned out to be full of tiny races. Rusty was telling me about this yesterday. He was like, oh, I actually physically yanked the power cable out of my machine 10 times, and in 4 of those 10 times, I got corruption. It's like, wow. And he's like, yeah, and I couldn't even reproduce it using a VM because of the way that the virtual machine works. It turns out you can't quite replicate this. So if we're expecting humans to try, human programmers, people who aren't Rusty or Tridge to get this right. I don't know. We've got to come up with some kind of help for these people.
Well, it's also because we're trying to be really cheap.
You know, every program is trying to be really cheap. Premature optimization is not only the root of all evil, it's extremely commonplace.
Which is why we live in Tridge and Rusty.
Which is why we should leave it to Tridge and Rusty. Which is, you know, why I'm going to be spending some quality time talking to Tridge and Rusty over, you know, how can we make sure that everyone in the world just uses TDB instead of some other data structure? Because I think that would be awesome. So here's another problem we've got. So there are two distinct kinds of observability, and this problem demonstrates it. So CPU A modifies a cache line. It says to the kernel somehow, okay, start syncing that out to the persistent memory. But right now the cache line is dirty in CPU A's cache. CPU B does a read to that cache line, and CPU A hands the ownership of the cache line over to CPU B. So it's observed CPU A's changes. Now the machine loses power. Someone tripped over the power cable again. On reboot, are we guaranteed that CPU A's changes are still visible after the reboot? CPU B got to see them. CPU B may have done something based on that. Maybe CPU B...
Journaling.
Sorry?
You need journaling.
We need journaling. You know, as a file system person, I'm sure you can tell me just how easy it is to get journaling right.
Nobody gets it right.
Nobody, file system people who specialize in journalism don't get it right. Stephen Tweedy got it wrong. Ted Cho got it wrong. You got it wrong. Everyone got journaling wrong.
The databases get it wrong too.
Every database I've ever worked on has got it wrong. It's, in fact, both of you, right? Both of you have got this wrong, right? Okay. We need to help people. I'm not smart enough to help user space people. I barely understand how other kernel programmers think. I certainly don't understand how user space programmers think. This is just going to be this huge challenge because, you know, we're going to get into a situation where everything works and works and works and works until that one day when you cut power and everything's corrupted and you don't know why and nobody knows why and
Then you start crying.
and you start crying. Absolutely. I mean, we're doomed with this stuff. We're utterly doomed. And yet I'm convinced this is the future of computing. And yet we're doomed if we do it. I kind of feel like we're in the same situation we were in with you know, when threaded programming started becoming common. Nobody understands synchronization. Nobody can do okay, Paul McKenney's laughing at me, I think, but other than Paul McKenney, nobody gets threading right. And yet we have somehow managed to get to a point where everyone's laptop has at least 4 cores in it. My phone is dual CPU. I understand the phones with like 8 CPUs in them these days. I mean, it's just ridiculous. We have somehow managed to come up with ways to help application programmers harness this power. I think there must be a way to help them with this as well. Do I want to go into this? Yeah, I should just go into this. All right. So I talked earlier about the APIs that we would be able to bypass the API for doing an I/O. You know, we just do loads and stores, and the things become persistent, and we don't need to do we don't need to tell some device go off and do a transfer. But the thing is that the current API we have insulates us from our bugs. Very easy to do a memory scribble. Dave Jones didn't quite manage to hit an oops earlier, but it's very easy for a user space application to pass an invalid pointer to the kernel, and because there's a missing security check, the kernel just goes and scribbles somewhere random. And If that crashes the machine, oh well. But if that corrupts the database that's stored on your machine, that's a problem. If it corrupts your favorite cat picture, that's probably a problem too. If it corrupts last Christmas, the photos you have of last Christmas, that's probably an even bigger problem, particularly if your granny wanted to see them again. So we have a situation where we're kind of oblivious to some of the corruptions that we see today, but they're going to become persistent and with us. So, you know, are we going to suddenly become able to write better software? Probably not. So I think we're going to need some tools to help us become resilient to some of these problems. Maybe it's a question of more checksums. Maybe we need to use erasure codes to help us gain reliability. So every time you access something, you just make sure that that nothing got corrupted. I don't know. Is this? Yeah, if we can persuade the hardware people to give us a copy on write, that could be interesting. And maybe we don't need them to. Maybe we can tell the MMU that everything is going to be read-only.
Well, as soon as you go to something like a copy on write approach, you can now snapshot your memory and roll back.
I love snapshots and rollback. I think that would be an awesome approach to take.
Starting to talk about persistent memory at this point. Somebody mentioned earlier checkpoint your CPU, snapshot your memory, checkpoint your CPU, restart from a known state.
Yeah.
If you're talking about persistent memory, we're talking about machines that don't need rebooting or booting as such. Once they're up, you've got a consistent state at all point in time. There's been plenty of research done into persistent computing in this sort of environment. So the thing that's been holding that back is that we just simply don't have persistent memory.
For that matter, one of the most painful thing with copy and write is the later cleanup required. But that would be a lot cheaper with persistent memory than it is with spinning media.
Yep.
Do you see this as the only type of RAM attached to the CPU? You think this will take the DRAM and this?
I think that's an excellent question, Dave. For those who missed it, he's saying, do I think that all memory is going to be persistent, or are we going to still have some amount of dynamic of DRAM? I don't know. I could see it going both ways, and I think it's going to kind of depend what exactly what comes out. I mean, some of these technologies are much closer to current DRAM than others are. Some of them, you know, reads and writes, they're like half the speed of current DRAM. So you wouldn't necessarily, so you'd really want to at least keep DRAM around as a cache. Maybe a write-through cache, but some kind of caching. If it comes out and it's only a couple of % slower, then you know that's definitely worth having.
But wouldn't there be sort of applications where you just need scratch space? You don't need this stuff to be persistent. So
Absolutely.
it seems to me that it's more a case of a system would still have something, you know, basically scratch RAM to work with, and you don't stuff you don't need to.
But it's fast enough, you may not care.
Yeah.
You may put in persistent RAM, you won't care if it never comes back.
Well, I mean, you have to just look at the way SSDs are implemented. Some of them use scratch space, you know, DRAM, and some of them don't. So, I mean, you're sort of talking about a similar sort of thing here. Some need it to be fast at what they're doing, some of them don't.
And if it consumes a lot less power because you don't need to refresh it constantly, you might be willing to live with it being half the speed.
Yeah, and some of these technologies are going to come in huge quantities, right? You're not going to be able to buy like these things in 1 gigabyte quantities. You're only going to be able to buy them in 1 terabyte quantities. And at that point, you know, the argument for putting DRAM in takes on, you know, an extra layer about, well, how much space do you need to have? Okay, so I'm going to close on a hopeful note. if we have persistent memory available to us inside the kernel, and we know it's persistent, one use we can make of it is recording logs directly, instead of asking the syslog daemon to read the D message and then copy it to a file in user space. And credit to James Bottomley for coming up with this particular use case. We do need some kernel API extensions, but they're pretty small and they make sense. Just a couple of tiny wrappers around code we already have. And the good news is we actually don't need to wait for persistent RAM to become available to test this kind of thing out. We can simulate it today using a normal file system. And I think this is a great use case, but I'm kind of intrigued to see if anyone else can think of other good use cases.
Not just logs, write the entire kernel, including its full state out.
Write the entire kernel, including its full state out. Right, so we're going back to what Dave was saying around basically just snapshot everything and on boot do a restore from S3, essentially. For debugging. I'm sorry? Crash dump, yeah.
More useful because you know your variable state at that point. If you're writing the entire kernel state.
Yeah, as long as we
I
could.
don't know why it got to that state.
But if you're talking about a system that's got a terabyte of this stuff, of course you're going to be using it as your main memory. I'm kind of working under the assumption that everything the kernel does is in the system memory. I mean, that's what we're talking about here. We're talking about stuff that doesn't have DRAM in it. Where are you going to store all of that kernel state? There's only one place it can go.
Looking at replacing DRAM altogether, yeah, for sure.
Depending on which of you think cold booting, right?
You only ever do that once.
You pull the plug and the cover comes back, hard lock again.
Can you reproduce the cache? Yes, in fact, it's all.
It's like, yeah, perfect.
My book is 100% reproducible. Here you are.
Here's the entire machine state.
Yeah.
Cold booting is like a feature, because at least you get back to sort of a known state of processes. So it's like this tricky hybrid approach there.
But I mean, look at what we're doing at the moment with our laptops, suspend and resume. You don't rip your laptop. I mean, up until a couple of weeks ago, I had 128 days uptime on my laptop.
Yes.
It's suspend and resume just works. Now, if that's persistent, all I'm doing is shutting the top and it's just shutting everything down.
Copying a whole bunch of device state and CPU state.
Yeah, but I mean, what I'm trying to say is that this persistence of our devices is pretty much already there. It already works. It's shutting down into a state that we can bring it straight back up. You know, so I don't see that there's going to be just this like little bit of something where we write kernel logs to it. So everything's just going to be in that RAM.
It's one right kernel log. You can just emails with 10
Well, you gzip it. You gzip it first, right?
You can do that, Jeff. We'll come down with a hammer or two. You know.
Yeah, products are going to suck.
Yes, sir.
If you have a stack of persistent RAM, then, or non-RAM, then it gets very tempting to go back to, say, the speculative execution models for functional programming and hold them around so that if the user does choose the option, the processing is already done. You know, you've got a stack of non-persistent memory. And of course, there's an energy cost to that is perhaps unacceptable. But yeah, and I think the other thing is that if you've, in some senses, what you've been asking for with your difference between persistence and coherence is actually transactional memory anyway, just rather than applied to RAM, applied to your persistent, your flash essentially. And in much the same way that you're enhancing your CPU currently for transactional memory for RAM, you extend those enhancements to cover you over on the flash drive as well.
That's really cool. I'm being totally taken back to my advanced computer architecture classes at university where they covered everything that wasn't a PC. I think there's a lot of good research being done on systems like that, and perhaps I need to go and reread some of that old literature back when people didn't think the whole world was a PC.
Yeah, I think there's some pushback further up the stack, in much the same way that the screen has forced us to look more into object-oriented programming. I think the abundance of CPUs forces more towards functional programming, moving from this obscure area of programming into more of the main line of the way things are done.
Cool, thank you. Yes, sir.
This is going to be really out there. 20 years ago, this was very simple to classify how people use the message pad. It had suits. It didn't actually have a file system. Could you repeat?
Just repeating. Oh wow, that sounded really good. The new message pad had soups, which were object-oriented abstractions for persistent storage. Now, that device totally took over the world, so take it as you will.
I've got one right here.
Yeah, but it was also one of the very first ARM PDAs, so, you know, maybe it's probably got ring-fenced of patents, but maybe it's worth having a look at some of the ideas behind it.
Yeah, I didn't have a Newton message pad myself. It's definitely something worth looking at. Fortunately, not with you.
No.
Paul. Oh, he's got to wait for the microphone.
Well, strangely enough, a lot of the computers I used early on had this property throughout all their RAM. It was called a core.
You know, I actually work with a guy who is of similar age to you, and he starts talking about core memory whenever I bring this kind of subject up as well.
So one of the things we were able to do was kind of like suspend and resume, but all you had to do was just turn the machine off, as was pointed earlier. The problem was, on the particular hardware we had, there was enough power surges in turning off and turning on that you maybe got to do it 5 or 6 times before something critical in your memory disappeared. And hopefully we've got a little better control of the electrons these days.
Yeah, not only better control of electrons, but I think we're just going to have such an abundance of this stuff that we're going to be able to afford to put in proper error correction and detection. At least from power glitches, not necessarily from stray writes.
But so the question is really strange to me because I remember when the computers were all that way and it wasn't that anybody did anything strange with them. So it's an interesting question.
Cool, thank you for that. Oh, yes. Go up. Up.
Yeah, thanks for that. Another interesting problem that's somewhat related is if you send your object up into space and it gets hit with all sorts of strange cosmic rays, then you still need to know whether the memory is what you thought it was, which goes back to your problem with the corruption of memory upon power down, power up, blah, blah, blah. But even in this case, corruption of memory whilst it's running. So I think whatever algorithm we work out for this problem would also be applicable to a spacecraft problem such as a satellite.
Yeah, absolutely, absolutely.
It's not just spacecraft, we have that problem with our routers. Because they run for a decade without stopping. And you're starting to talk about machines with that sort of uptime.
One would hope so. I would like to see machines with that kind of uptime.
Cosmic rays have been a problem on terrestrial computing anyway for quite some time.
Yeah.
There was a proof back in, I think, 2002 that memory corruption was being caused once a week on big supercomputers simply because the footprint of them and the frequency of cosmic ray strikes in that footprint of the Earth correlated exactly to the number of uncorrectable memory errors that were occurring in them.
And people in the US would radon in their basements.
The other cool thing when I was at HP has 2 major campuses, one in Cupertino, one at Fort Collins, which are about a mile different in altitude, and the number of corruption events were significantly higher in Fort Collins than they were in Cupertino.
Interesting amount of problems to be had by registering domain names that are 1 bit off of like
we're at the end of our time. I'm obviously going to be delighted to talk about this the rest of the week. Thank you all for coming, and I hope you enjoyed.